electric drive systems. The primary electric drivetrain components for fuel cell vehicles are the same as those for any electric vehicles: traction motors, power electrons, and batteries. Electric drive components require their own sets of auxiliaries and management systems for control and cooling of the equipment. A fuel cell vehicle may have a hybrid powertrain in which the fuel cell is sized at less than the vehicle's peak power requirement, and additional power is supplied from an electricity storage device such as a high power battery or ultra capacitor. Although a hybrid powertrain is more complex than one using a fuel cell alone, it offers advantages of regenerative braking, which helps vehicle efficiency and the availability of greater power for startup and auxiliary loads. Hybridization also would have an economic advantage if the cost of the peak power from the electricity storage device is less than that of meeting the power peak requirements with a fuel cell alone. In this video, I am going to explain the electric vehicle drivetrain. The contents in this one is what is the transmission configuration, what are the components of drivetrain, and what are the latest advanced technologies available in this electrical vehicle drivetrain. This slide shows the general configuration of an electric vehicle. A conventional engine-driven vehicle uses its engine to translate the fuel energy into the shaft power, directing most of this power through the device train to turn the vehicles. Much of the heat generated by the combustion cannot be used for work and is wasted, both because heat engines have the theoretical efficiency limit. Moreover, it is impossible to reach the time theoretical efficiency limit because some heat is lost through cylinder walls before it can do work. Some fuel is burned at less than the highest power possible pressure, and fuel is also burned while the engine is experienced negative load during braking or when the vehicle is coasting or at a stop with the engine idling. There are many possible electric vehicle configurations due to variations in electric propulsion and energy sources. Based on these variations, 6 alternatives are possible. In this figure, a single EM configuration with a gearbox clutch is shown in this figure. It consists of an EM, a clutch, gearbox, and the differential. The clutch enables the connection or disconnection of the power flow from electrical machine to the wheels. The gear consists of a set of the gears with the different gear ratios. Box and clutch is shown in this figure. The advantage of this configuration is that the weight of the transmission is reduced. The electric vehicle drivetrain alternatives based on the power source configuration. Besides the variations in the electric propulsion, there are other electrical vehicle configurations due to variations in energy sources. There are 5 configurations possible. They are: configuration 1. It is a simple battery powered configuration. The battery may be distributed around the vehicle, packed together at the vehicle back or located beneath the vehicle chassis. Configuration 2. Instead of the 2 batteries, this design uses 2 different batteries. One battery is optimized for high specific energy and the other for high specific power. Configuration 3. The battery is an energy storage device, whereas the fuel cell is an energy generation device from air. Configuration 4. Rather than storing it as a compressed gas, a liquid, or a metal hydride, Hydrogen can be generated on board using liquid fuels such as a methanol. In this case, a mini reformer is installed in the electric vehicle to produce necessary hydrogen gas for the fuel cell. Configuration 5. In fuel cell, the battery combination. The battery is selected to provide high specific power and high energy respectively. In this configuration, a battery and supercapacitor combination is used an energy source. This slide shows the electric vehicle drivetrains, ensuring effective power transmission at a high torque through manufacturing solutions designed for the requirements of electric vehicle drivetrain systems. Compared to the development process for traditional combustion engine vehicles, e-mobility is driving sustainable change in the way of manufacturer approach drivetrain design, where previously 6-speed manual or 8-speed automatic transmissions were standard in the automotive world. State of the art of electric vehicles use different kinds of the automatic transmission such as two-stage greater drives, integrated stepped planetary gear drives, or continuously variable transmissions, and also known as shiftless transmission to operate at optimum efficiency. Often, electric motors, power electronics, and drivetrain share a single housing, reducing the overall number of components in the powertrain and lowering the overall weight of the system. In the battery electric vehicles, this integrated unit may directly power a combined electric axle drive. In hybrid electrical vehicles, various transmission configurations are possible depending on how the manufacturers intended the electric motor and combustion engine to interact with each other. While many operating principles for electric vehicles drivetrains differ from their counterparts in combination or combustion engine vehicles, on the components level, there are actually many similarities in the design and manufacturing process required. The key components like straight gears, helical gears, and housings are common to both types of the drivetrain. The main challenges in the specializing such components for electric vehicle drivetrains are to deal with the higher torque and speed of the rotation that can be realized with electric motors. The tolerances involved in the precision manufacturing of the transmission components like straight and helical gears or planetary gear drive systems are typically tighter for electric vehicle components. The surface finish of gears also gains new importance as the noise emission of the drivetrain is critical in electrical vehicles due to the silent electrical motor. Hexagon has considerably experience in the development of the powertrain components in both automotive and aerospace sectors and is well placed to the support manufacturers throughout the development of the electric vehicles drivetrains. And simulation solutions enable manufacturers to optimize the gear and bearing design, model development and model durability, simulate lubrication efficiency, and access noise emissions before vehicles go into the development. The production software solutions both validate production process and ensure precision manufacturers of tight tolerance transmission parts, while our ultra high accuracy measurement systems are specified for inspection and quality assurance of critical parts like gears, shafts, and chassis. This slide shows the introduction of hybrid drivetrain. The term hybrid vehicles refers to a vehicle with at least two sources of power. Hybrid electric vehicle indicates that one source of power is powered by an electric motor There are many types of the hybrid electric vehicles such as the gasoline ICE and battery, diesel ICE and battery, battery and FC, battery and capacitor, battery and flywheel, battery and battery hybrids. Coming to the series hybrid system, in case of series hybrid system, the mechanical output is first converted into electricity using a generator. Conceptually, it is an ICE assisted electrical vehicle. The advantage of series hybrid driven systems are mechanical decoupling between the ICE and driven wheels allows the ICE engine operating at its very narrow optimal region. Nearly ideal torque speed characteristics of the electric motor makes multi-gear transmission unnecessary. However, a series hybrid drivetrain has the following disadvantages. First one, the energy is converted twice and this reduces the overall efficiency. Next one, the two electric machines are needed and a big traction motor is required because it is the only torque source of the driven vehicles. Coming to the parallel hybrid system, the parallel hybrid electrical vehicles allows both ICE and electric motor to deliver power to drive the wheels. Since both the ICE and EM are coupled to the drive shaft of the wheels through two clutches, the propulsion power may be supplied by the ICE alone, by EM only, or by both ICE and EM. The advantages of parallel hybrid drivens are both engine and electric motor directly coupled torques to the driven wheels and no energy form conversion occurs, hence the energy loss is less. Next one, compactness. Compactness due to no need of the generator and smaller traction motor. The drawbacks of parallel hybrid drivetrains are mechanical coupling between the engines and the driven wheels. Thus, the engine operating points cannot be fixed in a narrow speed region. The mechanical configuration and the control strategy are complex compared to the series hybrid drivetrain due to its compact characteristics. Small vehicles use parallel configuration. Most passenger vehicles employ this configuration. And coming to the series parallel system, in the series parallel hybrid, the configuration incorporates the features of both series and parallel hybrid electrical vehicles. However, this configuration needs an additional electric machine and planetary gear unit, making the control complex. The complex hybrid system involves a complex configuration which cannot be classified into the above three kinds. The complex hybrid is similar to the series parallel hybrid since the generator and electric motor is both electric machines. However, the key difference is due to the bidirectional flow of electric motor in complex hybrid and the unidirectional power flow of the generator in the series parallel hybrid. The major disadvantage of complex hybrid is higher complexity. Due to variations in the hybrid electric vehicle configuration, different power control strategies are necessary to regulate the power flow or from the different components. All the control strategies aim satisfy the following goals. First one, maximum fuel efficiency. Next one, minimum efficiency. Third one, minimum system cost. Fourth one, good driving performance. The design of power control strategies for hybrid electrical vehicles involves different configurations such as first one, optimal ICE operating point. The optimal operating point on the torque speed plane of the ICE can be based on maximization of the fuel economy, the minimization of the emissions, or a compromise between the fuel economy and emissions. Second one, optimal ICE operating line. In case of the ICE needs to deliver different power demands, The corresponding optimal operating points constitute the optimal operating line. Now coming to the power flow control in hybrid system. In series hybrid system, there are 4 operating modes based on the power flow. Mode 1, during startup, normal driving or acceleration of the series hybrid electrical vehicle, both the ICE and battery delivers the electrical energy to the power converter, which then drives the electric motor and hence the wheel through transmission. Mode 2, at light load, the ICE output is greater than that required to drive the wheels. Hence, a fraction of generated electrical energy is used to charge the battery. The charging of the battery takes place till battery capacity reaches the proper level. Mode 3. During braking or deceleration, the electric motor acts as a generator, which converts the kinetic energy of the wheels into electricity, and this is used to charge the battery. Power flow control in hybrid parallel system. The parallel hybrid system has 4 modes of operation. These 4 modes of operation are: mode 1, during startup or full throttle acceleration, both the ICE and the EM share the required power to propel the vehicle. Typically, the relative distribution between the ICE and the electric motor is 80 to 20%. Mode 2. During normal driving, the required traction power is supplied by the ICE only and the EM remains in off mode. Mode 3. During braking or deceleration, the EM acts as the generator to charge the battery through the power converter. Now coming to the power flow control, series parallel hybrid. The series parallel hybrid system involves the features of series and parallel hybrid systems. Hence, a number of operation modes are feasible. Therefore, these hybrid systems are classified into 2 categories. First one, ICE dominated, and second one, EM dominated. The various operating modes of ICE dominated systems are: mode 1, at startup, the battery slowly or single provides necessary power to propel the vehicle and the ICE remains in off mode. Mode 2, during full throttle acceleration, both the ICE and the EM share the required traction power. Mode 3, during normal driving, the required traction power is provided by the ICE only and EM remains in the half state. So the complex hybrid electrical vehicle configurations are 2 types: front hybrid, rear electric and rear hybrid. Both configurations have 6 modes of operation. Mode 1, during startup, the required traction power is delivered by the EMs and the engine is in off mode. Mode 2, during full throttle acceleration, both the ICE and the front wheel EM deliver the power to the front wheel and the second EM delivers the power to the rear wheel. Mode 3, during normal driving, the ICE delivers power to the propel the front wheel and drive the first EM as a generator to charge the battery. So power flow control hybrid control. So the complex hybrid vehicle configuration are 2 types: front hybrid, rear electric, front hybrid and rear hybrid. Both configuration has 6 modes of operation. Mode 1, during the startup, the required traction power is delivered by the EMs and engine is in off mode. Mode 2, during full throttle acceleration, both the ICE and the front wheel EM deliver the power to the front wheel and the second EM delivers the power to the rear wheel. Mode 3, during normal driving, the ICE delivers the power to the propel the front wheel and to drive the first EMA as the generator to charge the battery. Electric vehicle configurations. Compared to the hybrid electrical vehicles, the configurations of electric vehicle is flexible. The reasons for this flexibility are the energy flow in the electric vehicle is mainly through flexible electrical wires rather than bolted flanges or rigid shafts. Hence, the general configuration of the electrical vehicles are shown in figure. And the electrical vehicle has three major subsystems: electric propulsion, energy source, auxiliary system. The electric propulsion subsystem comprises of the electronic controller, power converter, electric motor, mechanical transmission, driving wheels. Electric vehicles demand has been increasing since the last few years. Vehicle powertrain is very important part of an electrical vehicle. What is powertrain? A powertrain is a set of components that generate power to move the vehicle. What is an electric vehicle powertrain? As the name suggested, this is a powertrain which is required to move an electric vehicle. Electric vehicle architecture mainly depends on electric vehicle powertrain design. So, electric vehicle powertrain is an important part of electric vehicle. And coming to the electric powertrain vehicle components. Now here is, over the past year, virtually all the world established automakers have announced or accelerated their plans for introducing new electric vehicles. The range includes everything from high-end luxury models to relatively low-cost entry-level offerings. Also, many well-funded electric vehicle startups are building new market entries into the ground-up level. While most of the media attention focuses on the big picture issues of how green energy electric vehicles are designed to help mitigate the climate change by the eliminating use of fossil fuels and will ultimately lower the cost of driving for consumers, there is another significance important that deserves the more alternation to this. Thus, this is the relatively simplicity of electrical vehicle powertrain and implications of the lower maintenance cost. Many electrical vehicles does not even need a transmission. Those that do use a much simple single speed system as opposed to the multi-speed gearbox in the gas burning vehicles. For example, Tesla electric motors only have two moving parts and use single speed transmissions with no gears. The company says its drivetrain has about 20 moving parts compared with the 200 in conventional drivetrains. Similarly, the all-electric converter bolt has 80% fewer moving parts than comparable car with the gasoline engine. Electric vehicles also does not need radiators, fuel injectors, gas tanks, valve trains or exhaust systems. You won't need to get an oil change, and due to the use of regenerative braking, you won't need to get your brakes changed as often either. While all these differences are major benefits to the customers and consumers, the impacts on the companies and workers in the auto industry are a mixing bag. Electric vehicles with simple designs and few parts are easier to build and more conducive to automated assembly. which can help manufacturers lower costs. Interplex is the proud to be an ongoing innovator in the development of new technologies such as battery systems, power modules, bus bars, solderless automotive interconnects, electronic control unit interfaces, sensor packaging, and many other advantages that are helping make a new generation electrical vehicles even more efficient to build, operate, and maintain. Coming to the next slide, and in this particular slide, in most electrical vehicles, the powertrain will have the components. First one, electric motor, battery pack, inverter, DC to DC converter, charger. Battery management system, BMS, manages the battery pack, so it is also an important part of the electrical vehicle powertrain. Coming to the electric motor is an important part of electric vehicle powertrain development because it converts the electricity to torque to move the vehicle. The torque is controlled by varying the current flow. Its efficiency is above 90% as compared to an engine whose maximum efficiency is 40%. Electric motor provides torque at zero speed, so a single gear ratio can be used between the motor and the wheel. The motor is controlled by electric vehicle motor controller. Coming to the next part, battery pack. Battery pack is the device for storing energy. It provides current to the electric motor as required by the driver. It provides direct current DC at the output terminal. Battery manufacturers, also with electric vehicle powertrain manufacturers, are doing a lot of research on this improving battery pack. Battery pack is one of the major contributors to the cost of an electric vehicle. Cost of battery pack continue to decline. And next component is inverter. As mentioned earlier, the battery pack provides the direct current, but the electric motor is controlled by alternating current AC waveforms. So, the inverter is used to convert the DC to AC and control the electric motor. Next component is DC to DC converter. Electric vehicles do use the 12 volts power system for the low power electrical components. The 12 volts system is powered by battery pack. A DC to DC converter is used to convert power from the battery pack voltage down to 12 volts. Next component is charger. Battery pack must be recharged. The recharge is done generally from the electrical grid. The charger does the rectification of AC voltage to DC voltage and controls the current flowing into the battery pack. Coming to the another component, that is the battery management system. As mentioned earlier, apart from the above mentioned components, battery management system is also important. It is an electronic control unit that is responsible for monitoring the entire functioning of the battery. It monitors the cell voltage, temperature, provides the thermal and overcharge protection, controls the battery charging, and etc. This slide shows the difference between electric vehicle powertrain and internal combustion engine. As can be seen from this table, the internal combustion engine vehicle powertrain is very complex and has many more components than an electric powertrain. Some of important difference between the internal combustion engine vehicle powertrain and electrical vehicle powertrain is shown in this particular slide. So, it is clear with the recent trends that electric vehicle powertrain is going to grow in the demand and would used extensively. Keeping the above points in mind, we have to covered that the electric vehicle powertrain so to its components difference between the ICE powertrain and electrical vehicle powertrains. This difference is shown in this particular slide. This slide shows the battery technologies. Battery electrical vehicles consist of a battery connected to an electric motor through an inverter and the motor controller. The automotive batteries generally operate on the DC current while the grid operates AC. A converter is needed to transfer power to the battery. One of the key advantages of an electric vehicle is its much higher levels of the energy efficiency. Typically, an electric vehicle will achieve the system efficiency of 80% from battery to wheel, while within the conventional IC engine, it's more likely 15 to 25%. This is largely due to the fact that the IC engine is a heat engine and much of all that heat is simply wasted. And furthermore, an IC engine tends to have a fairly narrow range of the power output over which achieves the maximum efficiency, which may not match the required torque. Stopping and starting in traffic as well as acceleration and braking also serves to waste the energy. By contrast, an electric engine does not comes with these shortcomings. Its efficiency is much higher and the torque range wider. Casing point 1 current was test driving electric vehicle as a while back. The every time I got to a hill, I took off the battery management system beyond disappears. One of the major disadvantages of this electrical vehicles that are relatively weight of the batteries compared to the equivalent tank of the fuel, about 40 times force per kg. Although this is the compensated by the greater power to the weight ratio of an electrical engine versus an IC engine. Not to mention the fact that the battery powered train is greatly simplified. Like I said, no gearbox, clutch, fuel system, and in some cases, no differential either. Also, there is a range of issues to consider. While the range of these electrical vehicles is steadily growing, however, while it takes a few minutes to refuel, a fuel powered car or electrical vehicle takes hours of the recharge. This is often leads to the phenomenon called range anxiety. Now, in other such examples, and perhaps the solutions of this particular electrical vehicles range problem could be hybrid cars, in particularly plug-in hybrids. Hybrid cars can broken down into the two general flavors, series and parallel. Now coming to the series hybrid, it is essential that is the electric motors drawing current from battery drives the wheels. The difference is that series hybrid has the engine some kind which is connected to the great generator rather than the wheels and keeps the battery topped up here. So given this range extended, typically operating at one set of the speeds. The major disadvantage of series hybrid is that it tends to be bit more of complex powertrain, given that a vehicle has all the hazard of both the ICE and electrical vehicles. Coming to the parallel hybrid gets around of these problems. In this case, the IC engine is connected to both the wheels but to an electric motor. It gains from regenerative braking and at low speeds, the electric motor can drive the vehicle without the IC engine. parallel hybrid systems tends to be much simpler, easier, and less costly and considerably less complicated to install here. One of the common limitations of both the series and parallel hybrid is the range under battery power. Now coming to the hydrogen cars. Generally, when we talk about hydrogen cars, we are referring to a series hybrid powertrain. The only difference is it runs on hydrogen instead of the diesel or petrol. There is a common micro conception that hydrogen car has to run on a fuel cell. However, there is no reason why hydrogen car cannot operate using a conventional IC engine set up to run on hydrogen. Similarly, a fuel cell car can run on petrol using a reformer to extract the hydrogen from the fuel. The main advantage of using a fuel cell is much greater thermal efficiency of the fuel cell. Fuel cells are also relatively quiet with no moving parts. However, while fuel cells are getting cheaper and more reliable for static applications, automotive fuel cells still come with a reputation for a lack of the reliability as well as the high cost. These points explains why how most of the fuel cell electrical vehicles currently on offer tend to larger or people carrier type vehicles. They simply need a much larger bucket choices or squeeze in the fuel cells, its controllers, all that series hybrid powertrain related gear, and those hydrogen tanks. Of course, the skeptic is quite curious whether the nice small high efficiency diesel car would actually achieve higher fuel economy and lower carbon emissions. This slide shows why our electric vehicles are catching fire. The Union government has constituted as an expert panel to probe the recent series of battery explosions in electric vehicles. Manufacturers like different manufacturers recalled some batches of the electrical scooters following fire incident involving the vehicles. And for example, last Wednesday, an 80-year-old woman died at his home in Telangana and Nizamabad district after the battery of an electric scooter exploded while being charged. After the inquiry, the Minister of Road Transport intends to issue guidelines for electrical vehicles, including tests for compliance with the safety norms. The growing concern over climate change has led to global efforts to affect electricity, the transportation sector. In parallel, cost of lithium-ion battery technology has decreased by a staggering order of magnitude in the last decade. The convergence of these two factors has resulted in a unique time in our history where we are the crush of a dramatic transmission or transition in the transportation sector will with electric vehicles poised to replace petrol vehicles.